In this video, we'll be talking about real numbers, intervals, and inequalities. But first, let's talk about what a set is. Much of calculus is based on properties of the real number system. In arithmetic, we learn facts about the real numbers and how we can perform operations with them. Algebra is an extension of arithmetic, so we begin this course with a discussion of the real numbers and their properties. A set is a collection of objects called elements of the set. Some sets can be described by listing their elements within these curly braces and separated by a comma. Example 1 says create a set containing the members of the hit K-pop group Blackpink. So typically we will call a set with a capital letter, and here I'm just going to call this set capital S, and that is for set, and this is going to be equal to, I'm going to draw a left curly bracket, and then I'm going to go ahead and list the members of the group and separate their names with a comma. So we have Jenny, Lisa, Jisoo, and Rose. And then I'm going to close it with a right curly bracket. So this thing here is a set, and this set has 4 elements because there are 1, 2, 3, 4 objects or things within this set. Now, the elements of a set can be anything. For us, the sets we will be interested in are those containing numbers. The set containing the numbers 1, 2, and 3 can be written as this. If we want to communicate a continuing pattern, we can use ellipses. Ellipses are the ... which means a continuation. So in this first set, we have 1, 2, 3, ... meaning that the pattern here, if you can see, is that we are increasing the whole numbers by 1. So the next number in the pattern or in the set would be 4, then 5, then 6. In this next set, we have 2, 4, 6. The pattern here is that we are looking at even numbers, so the next number would be 8, and then 10, 12, and so forth. Now, this set here, we have ellipses on both sides, so we would be going in both directions, and the next number to the right would be 16 because we're doubling the value each time, and essentially everything in that set is a power of 2. So the last set above, which is highlighted currently, contains all powers of 2. We will talk more about powers soon. One way to determine if a number is an element of this set is to ask, is it a power of 2? If the answer is yes, then it belongs to the set. If no, then it does not belong to the set. For example, the number 8 is in the set because 8 is equal to 2 times 2 times 2, which is 2 cubed. But 5 is not a member of that set because 5 is not a power of 2. There are a couple of ways to write this set based on the rule that it can only contain powers of 2. So let's write this in a few different ways. So I'm going to put the curly bracket, and I'm just going to put some variable. And the variable maybe I could use is x, and then I'm going to put a vertical bar. This vertical bar means such that. So I'm just going to indicate here, this vertical bar means such that. So we have values of x such that x is a power of 2. So it turns out that I could just write a sentence like that. And this set describes this highlighted set here because it contains everything that is a power of 2. Another way that I could describe this set is I'm going to have my left curly bracket, and then I'm going to write 2 to the power of n, where n, or such that n, is an integer. And then I'm going to close my curly bracket. So this is another way I could have written that highlighted set above. So this is called set builder notation. It's very useful in succinctly indicating the elements of a set. A final piece of notation before moving on to numbers is a shorthand way of saying an element belongs to a set. If A is an element of the set S, we can write A, and it kind of looks like a C with a horizontal bar in the middle, and then S. So this means A is an element of the set S, or A is in S. And then if it's not in the set, then we would write basically the same thing, but now I would put a diagonal slash through the middle symbol. So if I do that, that indicates that A does not belong in the set S. So going back above, so here we have example 1 that we were looking at previously. Using that set notation, I can say that Lisa is an element of the set S, because as we can see, Lisa is right here. Now, as much as I would like to be, I can not claim that I am in the set S because I am not a member of Blackpink. So we would say Mr. Kwon does not exist in the set S because I am not one of those 4 elements of that set. So now let's talk about the real numbers. Let's review the types of numbers that make up the real number system. The first kind are the natural numbers, which are denoted by the symbol. It kind of looks like an N with an extra vertical bar. So this is the symbol for the natural numbers. Also known as counting numbers, since these are the numbers used for, you guessed it, counting things. These are the numbers. So we have 1, 2, 3, 4, 5, 6, and so on. Next, we have the integers, denoted by, it looks like a capital Z, and then it has this extra bar here. So integer is a Latin word meaning whole, and the Z comes from the German word for number, which is Zahlen. The natural numbers are sometimes referred to as the positive integers, which, along with their negative counterparts and 0, make up the integers. So the integers, again, are all positive, negative, whole numbers, and also 0. 0 is neither positive nor negative. That is something to keep in mind. Okay, take any integer a and any integer b and write it as a divided by b. This is called a rational number, and it's denoted by, it looks like a Q, with, you guessed it, a vertical bar there. So that is the symbol for the rational number, or the set of rational numbers, and Q is for quotients. Also known as a fraction, these numbers make up a big chunk of the real numbers. And the real numbers is a capital R with this extra vertical bar there. Numbers that are real but not rational are called irrational numbers. They cannot be expressed as the ratio of integers. Some examples of irrational numbers include the square root of 2, pi, e, and the 4th root of 7. Here's a really nice graphic about how the various numbers exist and make up the set of real numbers. So a natural number is also an integer is also a rational number. And then notice that rational numbers and irrational numbers are disjoint, meaning a number has to be one or the other. It cannot be both. So every real number is either rational or irrational. We visualize real numbers by putting them on the real number line. So here is the real number line. And right now we can see the integers between -3 and +5, and then we've just placed some numbers on the real number line, like pi. Pi is irrational, and it is approximately equal to 3.14, so that's why we're placing it here between 3 and 4. And then the square root of 2 is also irrational, and it's approximately between 1 and 2. We have 1/2 and -1.75. Now, sometimes students will get confused. Take a moment and ask yourself, do you think that the number 1.5 is a rational number? Can I represent this as a ratio of 2 integers? And the answer is yes. 1.5 looks like a decimal, but we can also represent this as a ratio or a fraction of 2 integers because this is the same thing as 3 divided by 2. So that's a ratio of integers, meaning that this number belongs in the set of rational numbers. So I can say that. Now, square root of 2 is irrational, and I cannot represent it as the ratio of two integers, so I would say the square root of 2 does not belong or does not exist in the set of rational numbers. Smaller numbers are on the left, larger ones are on the right in terms of the real number line. Take two numbers a and b on the number line, then we can assign one of the symbols in the table below based on their relative positions on the line. So here, except for the equal sign, the other four are called inequality symbols. So these are called inequality symbols. And we use them to compare two or more values. So the very first row in this table says a is less than b. That means a is to the left of b on the number line. So for example, if I have my number line here, here is the number 3, and here is the number 5. So I would say 3 is less than 5. And you can read through the other ones. Let's go ahead and skip down where it says one way relations can be of use is to help us describe sets of numbers. For example, suppose we want the set consisting of the first 25 natural numbers. We know that we could write this set as 1, 2, 3, 4, etc. But writing out 25 numbers, that takes a long time. So alternatively, we could write this as the set where x is a natural number such that we have 1 is less than or equal to x, which is less than or equal to 25. And then I'm going to close my curly bracket. So instead of having to list out every single element like this is a much more compact, efficient way of writing that same set. And so we'll see more examples of this later on. Now let's move on to talking about intervals and interval notation. If we want to look at a segment of the number line, say all real numbers to the right of 3, up to and including 7, we can write the set S equals, open curly bracket, x is an element of the real numbers, such that 3 is less than x, and x is less than or equal to 7. This is an example of an interval. An interval is a line segment of the real number line. We can visualize intervals by shading part of the number line. For example, the interval above can be drawn as, so I know that I want to include 7, so what I'm going to do is I'm going to place a closed circle on 7, and then on 3, because we're not including 3 in the set, I'm going to place an open circle at 3, and then our set also includes every number between 3 and 7, so I'm going to go ahead and shade or color in everything between those. So this is how we would visually on the number line draw the set that we are describing here. The open and closed circles indicate whether the endpoints of the line belong to the interval or not. Since S contains numbers strictly bigger than 3, 3 is less than x, then 3 is not an element of the set S, and so we have an open circle. The inclusion or exclusion of endpoints in an interval determine whether or not the interval is an open interval or a closed interval. An open interval does not contain its endpoints, whereas a closed interval does. Intervals are important sets, and so as is common with important objects in math, they get their own notation. We simply refer to it as interval notation. So here is a table containing a bunch of interval notation. So this should say interval notation. And this first example is an open interval because it does not contain its endpoints. And so if I write parentheses a comma b close parentheses, that is this set in set notation. So it's all real numbers x such that x is greater than a and less than b. And then in the next column over, we can see that the graph on the number line is, I would put open circles at a and b and then shade everything between a and b. And you can see that there are many more variations of this, including intervals that involve infinity. Now, something to note that is very important is for infinity and negative infinity, you can never put brackets on them because a set cannot contain infinity because infinity is not a number. So whenever referring to infinity and negative infinity in interval notation, they must always have parentheses around them. Parentheses indicate that the thing that we're looking at is not included in the set, and brackets indicate that the thing that we're looking at is included. So again, for infinity and negative infinity, they must always have parentheses around them because a set cannot contain them. They are not numbers, they are an idea or a concept. We will generally concentrate on our sets being intervals on the real line, given two intervals, say, from A to B and C to D, where A to B is an open interval and C to D is a closed interval. We can construct two new sets called the union and the intersection. The union, we can combine or glue together the intervals and produce a set whose elements consists of all elements in each interval. The symbol for union, it looks like a capital U. The intersection is we can look at the overlap of each interval and produce a set that contains the elements that lie in both intervals. The symbol for intersection looks like an upside down capital U. Okay, so below we can see here we have two intervals. Here's our open interval from A to B, and here is our closed interval from C to D. Now in the blue at the very top, we have the union of the two intervals. Basically, we're looking at every single number that is in either set and then combining them to glue them together to form this new union set. In the bottom, in the yellow, we're looking at the intersection, which is the overlap of the two sets. So let's look between these two sets in the green and red. This does not contain A, so since it's not in A, it cannot be in the intersection, which is why we have an open circle there. But D, this value here, is in both sets. It's shaded in both the red and the green line, so it must belong in the intersection, and so that's why we have a closed circle on the yellow line. Something important to note is that the union of two intervals does not need to be a continuous interval. For example, the union of the closed interval from 1 to 2 and the closed interval from 3 to 4 will not be a single line segment. In this case, we write the union as 1 to 2, union symbol 3 to 4. If there is an overlap, we look at the closed interval from 1 to 3 and 2 to 4, then we can simply write the result and simplify it as 1 to 4. The final thing to note is that if two intervals do not overlap, again consider 1 to 2 and 3 to 4, then their intersection is empty, denoted, basically it looks like a 0 with a diagonal slash through it. That's called the empty set. And so we would say the intersection of these two sets is the empty set because they have no overlap between them. Example 2 says, consider the sets A is equal to Harry, Hermione, Ron, Hagrid, Dumbledore, Snape, and B is equal to the set Leslie, Donna, April, Andy, Jerry, Ron, Tom. We want to find A intersect B and A union B. So let's start with A intersect B. What we want is we want to look at the two sets and see what they have in common or what their overlap is. So the only items or elements I see in common are we have a Ron in both sets. So that means that the intersection of the sets A and B is going to be the element Ron or the set Ron. Now, A union B is we are taking an element from each set or any element from each set, basically combining all of them together to form a single set. Okay, so I didn't want to type out every single element. So here I have here A union B is equal to, and then I have every single element listed out from either set. Notice that even though Ron is in both sets, I only listed Ron one time because you don't need to duplicate, so I'm just going to list it once here. Example 3 says, simplify the following sets if possible. For part A, we have the interval from 10 to 20 intersect the interval from 8 to 15. So what I'm going to do is I'm going to go ahead and draw out a number line so we can see where these two sets have overlap. Okay, so I've gone ahead and I've, on my number line, drawn my two intervals. The first interval I've drawn in pink and the second one I've drawn in blue. And so remember, the intersection is where these two intervals or sets overlap. And essentially another way of thinking about that is, where do they have dual color? What numbers have both pink and blue on them? So I can definitely say that 10 is in the intersection because it's both blue and pink. So 10 is the smallest number that the intersection contains, and then we're going to go all the way to 15. But notice that 15 is not part of the blue set because there's an open circle there, and so I would put a parenthesis here. So there's our answer for part A. For part B, now we want to include any number that has any color on it because we want to take numbers that exist in either set. And so the smallest number we're looking at occurs here at 8, and the largest number that occurs is 20. But notice that on both 8 and 20, we have open circles. So I'm going to put 8, 20, and both of my endpoints should have parentheses on them because we're not including either of those numbers since they don't belong to either of these sets. Okay. Example 4 says, come up with two sets A and B such that A intersect B is equal to the empty set and A union B is equal to the interval from 5 to 10. So we want to come up with two sets A and B where they have no numbers in common because their intersection is the empty set. So first off, I want to say that there's infinitely many possibilities to get a correct answer here, and we'll just come up and give maybe one or two. So we don't want either of the sets to have any overlap because their intersection is the empty set, and we want it so that when we combine the two sets, they make 5 to 10. So how about I do 5 to 6, and I'm going to include 6 here. And then in my second set, I'm going to have it start at 6, but we don't want it to include 6 because if I put a bracket there, then 6 would belong in the intersection, but we want the intersection to be empty. And then I put 10 here with a closed bracket. So these are two sets A and B where their intersection is empty and their union is 5 to 10. So this is one possible answer that you could give. There's many you could give. Let's do another one. What if I did 5 to 7? I don't want to include 7 in this set, which would mean that I would have to include 7 in the second set, and it would look like that. So here's another possible answer for example 4. Let's talk about linear inequalities. Example 5 says, let's say that your mom tells you to go to the store and buy at least 8 bananas because she is making banana bread, but you know that you are going to take 3 bananas for yourself. How many bananas can you buy? Well, first off, let's say that the variable b equals the number of bananas you buy or purchase. So if I were making an inequality out of this, I know that the number of bananas that you purchase, if you subtract 3 from them, that has to be at least, which is another way of saying greater than or equal to the number 8. So what are the possible amounts of bananas that you can buy? Well, inequalities work very similar to solving equations. So if I added 3 to both sides, then that would give me the new inequality, b is greater than or equal to 11. So as long as you buy at least 11 bananas, you are in the safe. So you can purchase any amount of bananas that is at least 11. So this here is the answer in inequality notation. Here's the answer in a sentence. There's two more ways that we could represent our answer, and one of them is in interval notation. So if I wanted the interval notation, that would be bracket 11 comma infinity. And so here is our answer in interval notation. And then the last one is if I wanted to graph it, here's the number 11 on my number line. I would put a closed circle there, and then I would shade to the right, meaning that I could get any number to the right of 11 or exactly 11. So those are the 4 different ways that I could represent my final answer for example 5. The scenario above can be solved using a linear inequality. A linear inequality is a mathematical statement that can be boiled down to the form ax plus b blank 0, where the blank can be filled in with one of the 4 inequality symbols, which let's remind ourselves. We have greater than, less than, greater than or equal to, and less than or equal to. So those are the 4 inequality symbols, and any of these 4 can be filled into this blank spot here, and then that would create what we call a linear inequality. Example 6 says solve the inequalities, give final answers in interval notation, and graph the solution on a number line. So part A, we have 5 minus 3x plus 6x is greater than 11. Notice that these two things here are what we call like terms, meaning that we can combine them. So I'm going to combine those, and that's going to give me 5 plus 3x is greater than 11. And if I subtract 11 on both sides, I just am doing this to show you that it's going to end up looking like this, but this isn't what we want to do to solve it. If I did this, we'd get negative 6, and then 3x is greater than 0. So now notice that this is in fact a linear inequality because it looks like ax plus b blank 0, where the blank is an inequality. But I want to isolate x, the variable, just like we would if we were solving 5 plus 3x is equal to 11. So I'm going to isolate x. The first step I'm going to do is I'm going to subtract 5 on both sides, and that's going to give me 3x is greater than 6. And then from here I can divide both sides by 3, and if I do that, I'm going to get x is greater than 2. So there's my final answer in inequality notation, but it also says that we want interval notation and to graph the solution on a number line. So in interval notation, that would be 2 to infinity, like that. And then if I were to graph this on a number line, here is 2. I'm going to put an open circle on 2 and then shade to the right. And so those are our 3 answers for part A. For part B, we have 6 times 7x plus 2 is less than or equal to negative 240. And our goal right now is to try and isolate x. So what we could do is we could start off by, notice that these are being multiplied, so I could divide both sides by 6. And if we did that, we'd be left with 7x plus 2 is less than or equal to negative 40. From here, I can subtract 2 on both sides, and then that's going to leave me with 7x is less than or equal to negative 42. And then from here, I can divide both sides by 7, and that's going to give us x is less than or equal to negative 6. So there's our answer in inequality notation. And then for interval, we'll have negative infinity to negative 6, and then we want a bracket because we are including negative 6. And then lastly, if we're graphing this, we have negative 6 here. I want to put a closed dot on negative 6, and then I want to shade to the left. So there is the final answer for part B. When you are solving an inequality, and if you reach a step where you're multiplying or dividing by a negative number, you must flip the direction of the inequality symbol. Example 7 says, solve the following inequalities, give final answers in interval notation, and graph the solution on a number line. So for part A, we have 252 is less than or equal to negative 4 times the quantity 1 plus 8x. So here I'm going to start off by dividing both sides by negative 4. That will give us negative 63. Now, because I divided both sides by a negative, remember this step where it says you must flip the direction of the inequality symbol when dividing or multiplying by a negative number. So I'm going to go ahead and flip the direction. So now we have negative 63 is greater than or equal to 1 plus 8x. I'm going to subtract 1 from both sides, and we get negative 64 is greater than or equal to 8x. And then if I divide both sides by 8, I get negative 8 is greater than or equal to x. If I wanted to, this is the same thing as saying x is less than or equal to negative 8. Let's go ahead and write that in interval notation now. So that's going to be negative infinity with a parenthesis on it up to negative 8, which we're including, and so I put a bracket on that. So there is my answer in interval notation, and then if we were to graph this, here's negative 8, and I'm going to put a closed circle on it, and I'm going to shade to the left. So there are our final answers for part A. For part B, we have 6x plus 8 times the quantity negative 3x minus 1 is less than or equal to negative 98. I'm going to start off by distributing in this 8. That is going to give us 6x plus, actually minus 24x minus 8 is less than or equal to negative 98. And 6x minus 24x, those are like terms, so that's going to give us negative 18x minus 8 is less than or equal to negative 98. I'm going to add 8 on both sides. That will give us negative 18x is less than or equal to negative 90. And then my last step, I want to divide both sides by negative 18. Because we're dividing by a negative, I must flip the inequality symbol. So we get x is greater than or equal to positive 5. In interval notation, that is going to be bracket 5 comma infinity parenthesis. And then if we are graphing this on a number line, I have 5 here. I'm going to circle with a closed circle on 5 and then shade to the right. And there is our final answer for part B. Now let's talk about compound inequalities. These inequalities that we have seen previously can be referred to as simple inequalities. Now, a compound inequality is a statement consisting of two simple inequalities. Example 8 says, in an earlier example, we said that your mom asked you to go to the store and purchase at least 8 bananas. Let's say that the next day she asks you to go back and purchase at least 4 bananas, but less than 9 bananas. Write the number of bananas that you can purchase as a compound inequality, then graph the inequality or solution set on a number line. So again, I'm going to define the number of bananas that you can get to be the value b. And b is going to be greater than or equal to 4, because you have to get at least 4, but less than 9. So this is the way that we would write this compound inequality, and it reads 4 is less than or equal to b, which is less than 9. And then if we want to graph this on a number line, here is the number 4, here is the number 9, and I would put a closed circle on 4, an open circle on 9, and then shade everything in between. So in theory, I can buy any value of bananas between 4 and 9, including 4 and excluding 9, which means I could buy 5.2 bananas if I wanted to. Let's look at some more real-world examples of when we might use compound inequalities. So the first example is the element mercury is in liquid state as long as its temperature is kept between negative 37 degrees Fahrenheit and 674 degrees Fahrenheit. So in the table below, this is an example of a compound inequality that is bounded. And if we're calling the temperature capital T, then capital T must be greater than or equal to negative 37 and less than or equal to 674. And if we were to graph that, here's negative 37, here's 674. I would put a closed circle on both of those, and I would shade everything in between. In the second example, we say the Medicare Part D prescription drug plan has a gap in coverage called the donut hole. In 2013, that meant a person's drug costs were covered by Medicare as long as they spent less than $2,970 or $4,750 or more. This is an example of a disconnected or disjoint compound inequality. And in the table, if we put that in inequality notation, we would write S, if that's the cost, we would say S is less than 2,970, or S is greater than or equal to 4,750. And if we were to graph that, notice that it will not be a single interval that we're graphing. So I would find 2,970 and then 4,750. I would place an open circle on the left here and then shade to the left. And on 4,750, I would put a closed circle and then I would shade to the right. Example 9 says solve each inequality, graph its solution on a number line, and state the answer in interval notation. So part A, we have negative 3 is less than or equal to 4x minus 7, which is less than 29. I'm going to start off by adding 7. And notice that I need to do this on both sides of both inequality symbols. That's going to give me 4 is less than or equal to 4x, which is less than 36. And then from here, I'm going to divide by 4, and divide by 4. And we get 1 is less than or equal to x, which is less than 9. So there's our answer in inequality notation. In interval notation, that's going to be bracket 1 comma 9 parenthesis. And then if we graph that, here's 1, here's 9. I'm going to put a closed circle on 1 and an open circle on 9. And there is our final answer for part A. For part B, we have negative 7 minus 7x is greater than or equal to 0, or 10 plus x is greater than or equal to 11. So notice here that we have two separate inequalities, and so I'm going to solve them individually. Here I'm going to add 7 to both sides, and we get negative 7x is greater than or equal to 7. Now I'm going to divide both sides by negative 7, and when we divide by a negative, we have to flip the inequality sign. And then in this one, I'm going to subtract both sides by 10, and I'm going to get x is greater than or equal to positive 1. And so if we kind of combine those, here is our answer for part B in inequality notation. In interval notation, that would look like parentheses, negative infinity, comma, negative 1, bracket, union, bracket 1, comma, infinity, parentheses. So that would be our answer there. And then finally, if we graphed this, I'd have negative 1 here, positive 1 here. I would put a closed circle on both negative 1 and positive 1, and I would shade to the left of negative 1 and to the right of positive 1. And there is our final answer.